Welcome to this lecture on Turing machines. In the lecture, we will discuss a theoretical model called Turing machines. A Turing machine is a mathematical model of computation that defines an abstract machine which manipulates symbols on a strip of tape according to a table of rules. This model is very simple, but despite the model's simplicity, given any compute algorithm, a Turing machine is capable of simulating that algorithm on the tape. The Turing machine was first invented by Alan Turing in 1936. With this model, Turing was able to answer two questions in the negative. Does a machine exist that can determine whether any arbitrary machine on the tape is circular? That means it freezes or fails to continue its task. Similarly, does a machine exist that can determine whether any arbitrary machine on a tape ever prints a given symbol? Thus, by providing a mathematical description of a very simple device capable of arbitrary computations, Alan Turing was able to prove the properties of computation in general. So here's an example of a Turing machine. The machine operates on an infinite memory tape divided into discrete cells. The machine positions its head over cell and reads and scans the symbol there. Then, as per the symbol, its present place in the finite table of user-specified instructions, the machine either writes a symbol, say for example a digit or letter from a finite alphabet, and two, either moves the tape one cell to the left or to the right. 3, as determined by the observed symbol and the machine's place in the table, either proceeds to a subsequent instruction or halt the computation. So Turing machines are part of the abstract notion of what we mean by a computer. First, we learn about finite state automata, a machine that can be in any given states, and make transition to other states based on input it receives. However, there are limitations to finite state machines, such as finite state machines cannot count. Then we discuss a model called context-free languages. They're slightly more powerful than FSAs. In addition to state transition, it also has access to a stack. Sometimes we call this push-down automata. With the stack, now we are able to solve more problems, such as recognizing a string that contains some number of A's followed by an equal number of B's. In other words, a string of the form A to the n, B to the n. Or we can check if an expression is formed properly by inspecting its left and right parentheses. So now we are on to a even more powerful notion called the Turing machine. That includes, in addition to a state machine, an infinite tape that can be traversed in both directions. All this is part of automata theory that defines different types of grammars that describes these automaton. More information on these topics can be found in a course in automata theory or course in theory of computation. So first, take a look at Church-Turing hypothesis. The Church-Turing hypothesis, or thesis, stated that an effective procedure can be implemented by a Turing machine. What is an effective procedure? Let's take a look. So we can give some definition of a procedure. A procedure can be a program that executes a set of instructions, and that program may or may not halt. On the other hand, an algorithm is a step-by-step procedure of solving a problem. An algorithm, we assume, will terminate if that algorithm is correct. So let us take a look at some examples of procedures and algorithms. So here's an example of an algorithm. It asks if a given number is prime or not. It's not hard to design an algorithm to find the answer. First, we check if the number is 2, something like this. We check if the number is 2. since 2 is the only even prime, only one check is needed. We just check each number from 3 to n minus 1 to see if they divide n. If one of them do, then it's not a prime. So here we express in computer code what we mean by a number dividing n. So we also note that we increment the I by 2 to hit only the odd numbers. In fact, we can make this algorithm more efficient by checking the devices only up to square root of n, but that is not the point of this lecture. So we will leave that discussion to an algorithms class. So now let's take a look at a procedure. On the other hand, a procedure is something that may not terminate. So suppose we have to write a program to check if a number is a perfect number or not. A perfect number is a number whose divisors add up to that number. For example, 6 would be 1 plus 2 plus 3. 1, 2, and 3 are the only divisors. 28 has divisors 1, 2, 4, 7, and 14, and they add up to 28. So checking if a given number is a perfect number is not that hard. We can find all its divisors and see if they add up to the number itself. So we can definitely write a program to check if a number is a perfect number or not. However, if you have to write a procedure to check if a given number n, is there a perfect number greater than n, that's going to be difficult. That's not going to be hard, but we cannot guarantee this program will terminate. For example, if you have to do this, we just go one by one. We'll just check the numbers n plus 1, n plus 2, n plus 3, and see if they are all perfect numbers. So we may find an answer if there's an answer, although it may take a while, but we are assuming unlimited memory and unlimited CPU capabilities. But if there's no perfect number greater than n, no one knows if this is true or not, because the question is, given n, does there exist a perfect number greater than n? We don't have a proof of that. Because of that, we don't know whether this procedure will terminate or not. So now we will define the notion of a Turing machine that can help us execute an algorithm like a modern machine. So we cannot guarantee that an algorithm implemented on a Turing machine will hold or not hold, but we can certainly write an algorithm to do a certain task. So let's assume that we want to understand how to build a Turing machine to solve simple problems. But before that, let's try to understand how a Turing machine works. The machine starts at some position of the tape. Let's say from A1, this is the first character, first input symbol, and from the start is 0. The machine moves to left or right, replacing symbols as defined by a transition function. So the transition function says if the machine is in state S1 and it reads an input A, move the machine to state S2 and write the symbol A at the position and change the state to S2 and move the control head to the right. So what we need to do is to define the transition functions such that there's a clear instructions on how to move to a halting state. So given a problem that we want to solve, we have to come up with the complete set of transition functions that allows us to define that program. So now let's take a look on how to design a simple Turing machine. So here's the problem. In this problem, you're asked to design a machine that does something really, really simple. It reads a tape of zeros and ones and change them to x's and y's. We know how to do this using a language like Java. It's very simple. We just go through the input. When we see a 0, we write x. If we see a 1, we write 1. Now, what we want to do is, how can we write an algorithm in this abstract machine called Turing machine that can do the same thing? So before we get to that, since we are familiar with finite state machines, let's design a finite state machine to solve this problem. So assume the input alphabet is 0, 1, the tape alphabet is 0, 1, xy. So given a tape of zeros and ones, we want to design this Turing machine that replaces each 0 with x and each 1 with y. So how many states do we need? I think we can solve this problem with just a two-state machine. So let's take a look at two-state machine. We have a state called Q naught. In Q naught, I will design the transition function such that we see a 0, we write an x and stay in Q naught. If I see a 1, I write a y and stay in Q0. Now here we assume that tape has another character called A, which indicates the end of the input. So if you read an A, we write A and go to an halting state. So now the next question is, how do we describe this using transition functions? So let's take a look at that. So in fact, now I'm going to take this finite state machine and try to design a bunch of transition functions that defines the Turing machine. So let's define the transition machine, Turing machine with the state transitions. So this one says that if you are in Q naught and if you see a 0, you write a 0 and you write an x and move to the right. So in the Turing machines, you always have to move to the right or to the left unless you're in a halting state. And the next instruction says that if you're in Q naught and if you see a 1, you stay in Q naught, but you write a y on the tape and move to the right. So in all these cases, we are moving to the right. Now, this one says, if you're in Q naught, if you see an A, we must move to a halting state and write A and just not move right or left. So our movement is done. So here's how the Turing machine may look like, may work. So here's a tape of a bunch of zeros and a bunch of ones bounded by two A's indicating beginning of the input and the end of the input. So in this case, I would start my state from Q naught from this first 0. And then since I see a 0, I will write an X and move to the right. And I see a 0 again, I write an X and move to the right. Notice I'm still in Q naught. When I see a 1, I will write a Y and move to the right. Write an X and move to the right. Write an Y and move to the right. Now I read an A. So at this point, we execute this instruction. I'm in state Q naught. I see an A. We halt. So here's how the tape has changed when you go from when your Turing machine terminates as it reaches the final A. So we'll take a look at more examples, and we will try to understand how to design Turing machines. And some of the upcoming examples in this video will be based on first looking at a finite state machine and then going into a Turing machine. So let's take a look at more Turing machines. This one says design a Turing machine that flips bits on a tape. That is, if it sees a 0, it writes a 1, and if it sees a 1, it writes a 0. So let's first design a finite state machine to solve this problem. This is in fact the same as before. We just use one state and halting state and flip the bits. So essentially we can start with one state, Q naught, and if you see a 0, we write 1 and then stay in the same state. If you see a 1, you write a 0 and stay in the same state. If you see the terminal symbol A, which is the end of the input symbol A, we will write the A back and stay in the halting state. So if you look at the Turing machine state transitions, we can write the following. F of Q naught 0, if you're in Q naught and your input is 0, you stay in Q naught and write a 1 on the tape, that is flipping this 0 bit into a 1 bit, and move to the right. Turing machines must continue to process input until it ends the input use with the character A. This one says if you're in Q naught and you see a 1, you flip the bit to 0 and move right. And if you see a A in the Q naught state, then you halt and maybe perhaps you write A back into the tape and then not go anywhere. So let's take another look at another problem where we have to design a Turing machine that prints E and halt if the number of zeros is even, and the prints O if the number of zeros is odd. We can also build a finite state machine to do this, so let's do that first. Assume the tape has some blanks other than zeros and ones. So let's do, first of all, a finite state machine. So we define one state, Q naught, which indicates that we have seen even number of zeros, and we define a state Q1, which indicates that we have seen an odd number of zeros. And clearly we can draw this finite state machine. If you see a 1, your number of zeros, the parity of the zeros hasn't changed, so you stay in Q naught. If you see another 0 when you're in the even state, you go to the odd state. And if you see a 0 in the odd state, you're coming back to the even state. And if you see a 1, you're going to be staying here because you're not changing the parity. So that's the simple Turing machine. Now, as it works on the tape, it'll go from 0, it sees a 0, it writes an X to indicate that it processed this 0. If you see a 1, it writes an X. So in other words, at the end of this, you don't have zeros and ones anymore, you just have X's. But depending on the state you're in at the final state, then you decide whether you have seen even or odd number of zeros. All right, so we will also define halting state, where we define that if you see the end character A, we write O because we're in the odd state. This means that you have seen an odd number of zeros. This means that you have seen an even number of zeros. Okay, so here's the state transition table for a Turing machine. We have Q naught, Q1, and our alphabet has 0, 1, A. And you can see that this table reflects what we see in this diagram here. So you can easily take a finite state machine and draw the Turing machine transition table. Let's take a look at a more interesting problem now. So build a Turing machine that adds 1 to a binary number input given on a tape. So what we mean by that is if you have a binary input on the tape, let's say 0, 0, 0. This indicates just the decimal 0, 2. If you add 1 to this, then it adds 1 to this bit and you get 0, 0, 1. So you can see that if you recall how to convert binary to decimal, this is the power 2 to the power 0, 2 to the power 1, 2 squared. And this indicates this is, in fact, the number 0. This is number 1. Now, if you look at this 1, and if you add 1 to this bit, 1 plus 1 is 0 and carry 1 because you're performing addition in base 2, we end up with 0, 1, 0. So in fact, you can recognize this as this is the decimal 1, this is the decimal 2. And if you get this number where we have 0, 1, 1, we add 1, 1 plus 1 is 0 and a carry 1, 1 plus 1 is 0 and a carry 1, and the carry 1 is placed there. You might recognize this as the number 3, 1 plus 2, and this as number 4. So if you add 1 to 3, you get 4. So essentially, we want to build a machine that can do this. Given a binary input, let's add 1 to it. So let's design the finite state machine first. So let's design 2 states. You can have other ways to do this, but let's just start with this. Let's just say that S naught means you don't have a carry to consider. S1 means you have a carry to consider. So, and S2, we need another state because after adding the first one, we need to move on. We cannot keep adding 1 to each digit. So this means that we assume that there's no more carry in the system and we can continue to write the current 0 or 1 from that point on. So that's our state S2. No carry to worry about state. That means you would output the same thing. So here's our transition table for S node and S1. So when you're in S node, that means you don't have a carry in the system. You get a 1. Now you have, because you're adding 1, so you have 1 plus 1, which would give you 0, and then you go into the carry state. Because adding 1 is like you already have a carry in the system even before you start. So if you see a 1, then you have to add 1 to it, so you get 0 and go to the carry state. Now, if you get a 0 in the no carry state, you only got a 1, which is from the, let's say we are trying to add 1, and then we just print 1, and there's no carry in the system. There's no carry to worry about. Now, in this case, if you get a 1 in the carry state, that means you already have a carry, and then you get another 1, that means you write a 0, 1 plus 1 is 0, but you still have a carry, so you're going to stay here. But if you get a 0 in the carry state, that means you have a carry, so you add 1 plus 0, and you output 1. Now you don't have a carry in the system, so you move here. So what happens here? Here, you just have to write, if you get a 0, you write 0. If you get a 1, you write 1, because there's nothing more to worry about. And at the end, you can halt the machine. So if you simulate this machine, you will see that if you start from the left, rightmost digit, 0, so we see a 0, we are in S naught. So when you see a 0, we write a 1 and go to no carry state. So that means this 1 is written. So now you're in S2. So then the rest of the bits, 0, 0, are written as it is because you're in S2 state until you get to the end of the input, which at that point you halt. Let's take a look at this one here. So here we see a 1, the rightmost bit. So if you see a 1, you print a 0, which is this one here, and go to the carry state. And now you have a carry state. Now you're in S1. And then you process this 0. Now when you process that 0, you're in the carry state. So you write a 1, which is this one here. So you write a 1 and go to no carry to worry about here, which is the S2. So now you're in S2. So you write a 1 and you're in S2. But in S2, you just process the bits as they come. So you can see that this also worked. So here's the transition table based on what we see here. When you're in S node and 0, this is the transition you have to do. Notice we are moving left because we are processing from the rightmost bit going back to the left. So this is how it works. If you see an A all the way at the left, we will say, okay, let's halt it and nothing to do, and we are done. All right, so next we're going to check how to build a Turing machine to check if an expression is well formed. So now we want to build a Turing machine to recognize a well-formed expression. As you can see, this one is well-formed. You have matching left and right parentheses in here. We know this can be done by a PDA, or push-down automata, which includes a finite state machine and a stack. So let's see how we can build this table by defining 3 states. So we want to build a Turing machine with 3 states, and you will understand why we need 3 states. And we will define the transitions for the characters left parentheses, right parentheses, A and X. So the basic idea is that we move right in Q naught as long as we see left parentheses. We keep moving to the right. And when we see the first right parentheses, we write an X. We process that and start moving left and switch the state to Q1. So now we wrote the X and we start moving to the left. So in Q1 is a left moving state. When we find it, we write the X. When we find the matching left parentheses, we write an X, and now we have processed a pair of things. So we're going back and forth between. So we find this one next, switch back to Q naught and go left and find this. And so now we have found matching parentheses. So in Q naught, you always keep moving right until you find a right parentheses. In that case, we write an X and start moving left in Q1. And now we find the left parentheses, we write X, and then we start processing, you keep moving right. So we're going back and forth between left and right parentheses until in Q naught we see an A. When we see an A, we know we have come to processing the end of it. So in A, we have to keep moving to the left. In other words, we switch back to Q2 now. In Q2, this means that we may have processed all the characters, and that's the state that indicating that Q2. And then in Q2, we just start moving to the left until we find the other A. If you find the other A and all the others are X's, that means we have successfully processed the expression. If you don't, if we find an unprocessed left parentheses, we know that the number of left and rights are not matching. So let's take a look at this one from 1 to 6. So starting with the leftmost parentheses, we rewrite the left parentheses and move right. We do not do anything until we see a right parenthesis. We also stay in state Q naught as long as we see left parentheses. And this is reflected in the table by this entry here. If you're in Q naught, we see left parentheses, just keep moving left. Keep moving right and keep rewriting the left parentheses. So now we see a right parenthesis. So if we keep moving to the right, we see a right parenthesis. So when we see a right parenthesis in state Q naught, which is what's going to happen next, we write an X to process that right parenthesis and change the state to Q1, start moving left. So that is reflected in this idea here. So when we see the right parenthesis, we switch the state to Q1, write an X to indicate that I have processed that right parenthesis and start moving left. Now we are in Q1, and in Q1, if we see a left parenthesis, we have found a match. So Q1 is moving left and we found a match. And so we write X and switch back to Q naught and start moving right. This is reflected in this entry here. You're in Q1, and if you encounter a left parenthesis, we write an X, that means we process the left, and then start moving right in Q naught again. So now when in Q naught, moving right, we encounter X's, these are all processed. So we might encounter X's in Q naught, these are all processed. And so we continue to move right in Q naught. This is reflected in Q naught XR. So Q naught XR, it says that if you see an X, that means those are the processed things. So just keep moving right in state Q naught until you see right parentheses or left parentheses, you keep moving left, right. So now let's see what happens. So what happens when you're moving left in Q2? So you keep moving left and right. So in Q naught, we move left. So in this case, once again, so the next idea would be that, so in 5, so like for example, if you're in Q naught and if you see an A, this means you have reached the end of the processing. So we write an A and start moving left. And if you start moving left and the in Q2, we might see a whole bunch of X's as we move left. So you're in Q2 now, switch to Q2, whole bunch of X's. So we keep moving left, rewriting those X's. This is reflected in Q2 XL. Now what happens is when we are moving left in Q2, when we encounter a left parenthesis, then that is not processed and the expression is not well formed. So for example, if you see a left parenthesis in Q2, we are not hoping to see anything in Q2. We switch to Q2 here. We're hoping to see all the X's. But if you encounter left parentheses, it's possible, and then you write a no and halt the machine. This should be just not moving left. This should stop the machine. So what's another error condition? Suppose we are in Q1, and Q1 is a left moving state. If you're in Q1, like you switch to Q1 in right parentheses, you might encounter a whole bunch of X's that had been processed. Just keep moving left and left and left, looking for that left parenthesis. So if you're in Q1, you switch to, you're looking for a left parenthesis to match. And if you don't find it, that means, if you don't find it, that means if you're in Q1 and if you encounter A, at the end, that means you didn't see that left parenthesis. So we must halt the machine and write no, and this should be no processing. So let me just change that here. So this is, we're not going anywhere in these cases, right? So you're halting the machine. So now let's take a look at the next stage. Suppose you're in Q1 and moving left, you might encounter a whole bunch of X that have been processed. So just keep moving left. And so that's reflected in this state here. So for instance here. Okay, so this one says that Q1, if you're in Q1 and you might encounter a whole bunch of X's in Q1, just keep moving left. When you see an X, just keep moving left. They have been processed. Now, so the final one is going to be that if you're in, now how do we know we are successful? There's only one condition that we are successful. We are successful if you're in Q2. Let me get my, let's get this one here. So if you're in Q2, and you're successful, if you're in Q2, that means you have seen the A. That's when you switch to Q2, you look, this is all X's, and you encounter the A at the end. So this means it is a success, and then we write this instruction, Q2, this instruction here, which says that if you're in Q2, if you encounter the A, this means that we are good. That means we have seen nothing, no unprocessed parentheses, and we can write the success Y and halt the machine. So that's how it works. And so in the video, we saw a number of different examples. Some examples we went over finite state machines, and then we formed the Turing machine. In some examples, like a left and right matching parentheses, this could not be done by a finite state machine, but it can be done by a PDA. So we didn't have to use a Turing machine to do this. But we saw another example before this where we had to add one to a given number. That can only be done by a Turing machine. There's no PDA or finite state machine that can do it. So you can see that we discuss several things, and in this lecture we focus on Turing machines and how they work and why they are reflecting of the modern computers. Okay, thank you for watching.